All right, so general theme of the talk is what is abstraction, how does it work, that sort of thing. First up, just some sort of general examples of what we're even talking about here. Example of the kind of abstraction we're thinking about would be something like gears. We have like some physical objects which are made of a bunch of molecules or whatever, and we abstract these into high-level things like gears, which interact with each other in high-level ways. Like these two gears, they rotate or whatever, and we just think of them as two sort of atomic things. Another example would be a street map. So like here's New York City, or rather a street map of New York City. What's the relationship between this and the actual streets in New York City, or my model of the actual streets in New York City? That's abstraction, right? This is a high-level abstract model of New York City's streets. Third example, an electronic circuit. If you've had like an electronics class or something, you may know the phrase lumped circuit abstraction, meaning we take a bunch of low-level materials like bits of metal or ceramic or whatever, and we abstract these into a circuit, which has wires connecting these black box components like resistors and capacitors and whatnot. Third example would be like here we have three lions. We like the physical lions, then we abstract them by various steps into like abstract lion objects, and we can abstract them even further into numbers, so on and so forth. So the general theme that I want to point to in all of these is that when we abstract things, we throw away information. So like in the gears example, we're throwing away information about all of the low-level molecules, their positions, their momenta, all that. Or in the street map example, we're throwing away lots of information about the physical streets, like what do the buildings look like? What's on the streets? What's the width of the sidewalk? All that gets thrown away in the street map. In the voltage example, circuit example, similar to the gears example, we're throwing away lots of low-level information about like what the metals are made of, what the internal structure of a resistor or a capacitor is. Or in the lines example, we're throwing away lots of detailed information about the lines themselves and just keeping around the fact that there's three of them. But in all of these cases, we're not throwing away all of the information. We're keeping around some high-level summary data that allows us to answer certain kinds of queries. So like in the gears example, we want to be able to answer queries about like the influence of this gear on something far away. Like maybe we have a gearbox here, and there's some wheel that these are turning outside. And we want to answer queries about like, if I turn this crank, how fast is this wheel going to turn? Or in the street map example, we want to answer queries like, how long is it going to take to walk from like over here all the way to over there, right? Or we want to answer questions about how far apart two things are, or the connectivity of the streets. In the circuits example, we want to be able to answer questions about like currents and voltage and whether a light over here is going to light up, right? And in the lines example, I mean, we can answer questions about numbers, right? Like, am I more likely to get eaten or less likely to get eaten based on number of lions? So the idea here is we're throwing away information, but we're keeping around some summary data that lets us answer certain kinds of queries. That's sort of a starting point for what abstraction is, how abstraction works, but that's not really enough. The problem is, in order for this to be practical, we can't just like keep around a giant list of all the queries that we can answer and all the queries that we can't answer using the information we have, because there's just too many possible queries. Like the number of possible queries we could run on some model is just exponentially huge in the size of the model. So what we need is some notion, some particular way of throwing away information that conserves the information needed for certain kinds of queries where we know in advance what class of queries is going to be conserved. Does that make sense to people? Nod. Nods. Okay, good. And the sort of thesis of this presentation, among other things, is that the information we keep around is information that's relevant far away in some sense. The gears example is sort of prototypical. Like if we look at all the atoms in this little chunk of the gear, the motions of these atoms isn't particularly relevant to predicting the motion of a wheel or something that's far away from the gear itself. except for a little bit of summary data about how quickly the gear is turning. So that's sort of the very short version of it. Outline the rest of the talk. We're going to go through a few examples of this, physical examples to start with, since they're sort of the simplest. We'll do billiards, an electronic circuit, and then talk about a pencil. Then we'll get to the math, and then we'll do a couple of thoughts on like how this applies to problems of living in a high-dimensional world, like our world. How this applies to science, how this applies to language, and then we'll wrap up with a interesting hypothesis. Cool. By the way, people are welcome to like interrupt or ask questions or whatever. I'm not really looking at the screen, so like you should yell if you want to. Otherwise, I'm just going to go. So, yeah. Cool. Other than that, I'm going to be speaking into a vacuum here. So first example is billiards, pool. So like, hopefully you've seen pool at some point. You hit the white ball with a cue. White ball goes rolling into the other balls, and they all bounce around. We'll start with a very simplified idea of pool, where we have a bunch of balls in a straight line. And we're just going to hit the cue ball head on. It's going to go rolling into this ball. That's going to go rolling into the next ball, and so on down the line. Interesting fact about this system is that small errors get amplified. So if I hit this white ball just slightly at the wrong angle, the next angle is going to be even further off center, and the next angle is going to be further off center still, and that's going to amplify exponentially until eventually these balls just are completely off the line, right? And this is actually a really, like, if you want to work this out mathematically, it's really simple. The key thing here is that the uncertainty or error in that initial angle gets amplified exponentially as the balls collide. And this generalizes to full like 2D pool or even 3D version. If you just have balls bouncing around in random directions or whatever, every collision, the error or the uncertainty in the ball's positions and momenta is going to get amplified, and is going to be amplified exponentially in the number of collisions. This is chaos. If you haven't seen chaos before, now you know what chaos is. Small errors get amplified over time as the system evolves. From an information theoretic standpoint, what this is saying is initially, if we imagine that these are like the coordinates describing the system, the positions and momenta of the balls, if we want to predict the first few significant digits of where the balls end up, then at first we only need to know the first few significant digits of where they started. Like the very fine details of this initial condition are not going to be very important for predicting the coordinates of the next ball. But as we go forward in time, errors get amplified, and digits further and further back start to become relevant to predicting these most significant digits in the coordinates later. So information theoretically, even though the system is reversible in principle, in practice, because we only have like finite precision in our measurements, our uncertainty in those measurements will eventually become relevant, and eventually will wipe out all of the signal from our measurements. So as things further and further back in the expansion become relevant, it's going to wipe out all of our signal from these first few digits, and we're going to become completely unable to predict the positions or momenta later on. Make sense? But it turns out that not quite all of the information is wiped out. The vast majority of information is wiped out, but there are certain quantities which aren't wiped out. As in, if we have like imprecise measurements of them to start with, those are still going to provide good information later on. In particular, for this system, this includes the energy. In an ideal billiard system, the energy is conserved. So if we have an imprecise estimate of the initial energy, that's going to provide us a good estimate of the final energy. That information doesn't get wiped out. We won't be able to predict, say, the position of a ball or the momenta of a couple of particular balls or anything like that, but we can predict the energy. And similarly, if like we're able to change the dimensions of our pool table, the volume is something that is conserved with each collision. So that information is not going to get wiped out. The number of balls is conserved. So if we know how many balls we started with, that information is not going to get wiped out. You put all this together, the information that's conserved, the information which is not wiped out by these chaotic interactions, are exactly the things you have in your ideal gas law. You've got an energy term, a number of balls term, and a volume term. And then other things are conjugates of those. So like pressure is just a conjugate of volume. Different way.
Back to the everything part. There's just other things that are conserved, like the colors of the balls and so on.
Yes. So if you have things like colors of balls or other things in the system, those would also potentially be conserved with the number of collisions. Yeah. And in fact, if you study like statistical mechanics, a common thing that you do is add in other conserved quantities whenever they're there. Okay. So the idea here is, going back to the idea of abstraction, our notion of far away is just the system at a later time. So we have the system at an initial time, we have system at later time, and if they're far apart in time, then most of the information is wiped out by chaos, except for these few high-level variables. And these few high-level variables are obviously much lower dimensional than the whole system. Like if we have a mole of atoms bouncing around in a box, then you have like 6 moles or 7 or 8 moles of variables describing that system. And yet there's only going to be like 3 or 4 or 5 variables that you need in your summary to get the best prediction you can of what's going on later. All the other information is just going to get wiped out. Make sense? Electronic circuits give us a similar example. So if we look at an electronic circuit at a low level, so like a transistor or something, looks sort of like this. You've got like a physical chunk of silicon here. You've got a couple pieces of aluminum going down to it, and you've got some doped regions. Apply a voltage on this piece, electrons get dragged up into there, gate opens, and this thing allows current to flow. So at the lowest level, at the physical level, you've got a bunch of actual chunks of material, but then we abstract that into a transistor. So like this little component in a circuit diagram, that's a transistor. So we're throwing away all the information about what's going on at this low physical level, but we're keeping around a sort of input-output relationship. We say like, if I apply X volts on this wire, then I'm going to have current flowing from here to here, and we have sort of a functional description of that, right? So in this case, our notion of far away is what's happening sort of physically far away from the transistor. Again, looking at this picture, if we measure voltages really close to this component, like right here, that functional description isn't going to be very good. We're going to get a little bit of backtalk from other pieces that are nearby. But as long as we're a little ways out, the same sort of chaotic motions that apply in an ideal gas are going to apply here. Like you're going to get chaotic motions of electrons and atoms just sort of jiggling around in here or whatever. And that's going to wipe out most of the detailed information of what's going on inside this gate. And what you're going to be able to measure far away is just these sort of voltages and currents that are going in and out. So that gives us what's usually called the lump circuit abstraction, where we have discrete components like this transistor or this resistor or this voltage supply, and they're connected by wires which just carry voltage and current. The idea being the voltage and current are the summary information, which is relevant to components far away. Everything else gets wiped out. Similarly, we could look at the next level of abstraction up, going from circuits to digital circuits. So like this right here is a NAND gate. And rather than thinking about all the low-level pieces of that NAND gate, we just treat it as a logical NAND. And then we have, rather than continuous voltages going in and out. We have discretized voltages going in and out. So like this is either a logical high or a logical low. And again, there's like a notion of far awayness that applies here.
John, I just want to object again because you once again said everything else gets wiped out.
Yeah.
And I wouldn't normally object to that, but because this conference is called Finding the Right Abstractions,
yep,
and our goal is to possibly identify abstractions that haven't yet been identified, I want us to like not stop our curiosity by saying everything is captured.
Yes.
So anyway, every time you say everything else is wiped out, I'm going to be like, give me your proof that everything else is wiped out. And then you'll probably say, never mind, well, we know these things aren't wiped out, and there might be more or something.
So whenever I'm saying everything is wiped out, the usual like implied bit there is that's relevant to particular other things in the system. So like, for instance, we know that everything is wiped out, which would be relevant to predicting, say, voltages and currents in this other component over here.
I don't think we know that.
We know this experimentally, and we know it because we designed the system to work that way.
All right, I'll put this till after the talk.
Yeah, so this is actually really important. This is a key design constraint in designing electronic circuits. If you have some system over here, and you look at the currents and voltages in these wires, if those currents and voltages have an effect on the wire over here, that's a leaking abstraction, and that's a design problem. Like, we have to design these circuits to not do that. And in fact, a huge amount of simulation is done in circuit designs to make sure that doesn't happen. So like enforcing the abstraction is a big deal. In the billiard system, similarly, for this particular system, there are actual proofs of this. You can prove that these are the only variables that are relevant at later times. Yes.
So from Andrew's question, I thought you were going to say something sufficient statistics. So
yes.
How do we know that something is that are the variables that we picked or these numbers or values that we picked are abstractify enough, or we can throw away this stuff? It's because the conditional expectation given the values of these sufficient statistics are sufficient in the sense that the conditional probability is the same as our previous distribution. Is something like that?
Yes, there's a simpler way to think about that we'll get to a little bit later in the talk. But broadly speaking, the idea is we're going to be checking things experimentally to verify that we actually have enough information. Okay. Other questions right now before I talk about a pencil? Yeah. So next example, pencil. Think about like, if I have a pencil here, what information about this pencil do I need in order to predict things about a pencil at a later time? Or what information do you need in order to predict things about this pencil? One interesting point is this pencil is a rigid body, meaning if I know where the center of mass is in space, that's 3 dimensions, and what angles it's at, so like that's 1, 2, 3 dimensions. If I know those 6 dimensions, then I can predict reasonably precisely where everything else about this pencil is. Like I can predict where that little chunk is, I can predict where that little chunk is, I can predict where that little chunk is, and so forth. So all I need is a 6-dimensional summary, and then I can predict reasonably precisely where all the little pieces of the pencil are. And of course, there's going to be some imprecision there, like the pencil can, twist a bit, or it can vibrate, or all the low-level atoms are sort of bouncing around a little bit. But that sort of information wouldn't usually be relevant far away anyway, because like from here, I don't have any way to measure the low-level vibrations of the atoms. Again, that's going to be wiped out by chaos, typically. And in this case, to Christian's point, we don't have a proof of that, but empirically, it looks pretty likely that we're not going to be able to predict motions of atoms based on information available from like a foot away from the pencil. So the idea there is we have this 6-dimensional summary that tells me most of what I want to know about this pencil, even though there's like a mole of atoms in it or something. So that's the conceptual model to have in mind. And later on, we'll talk more about like kinds of evidence we have for this or places where this is useful. But right now, we're just going to dive into formalizing these ideas. Okay. Nods. Yeah, good. Falling, not asleep. All right. So I'm going to formalize this in terms of probabilistic systems. I expect there are people here who will come up with more general ways of setting it up that are possibly better. But usually probabilistic systems work for at least most of the sorts of things that I'm thinking about. So in terms of probabilities, the idea is we have some low-level causal model. So like these arrows these tiny arrows here are all causal arrows. So this would be like the dynamics governing all the atoms in a pencil or something like that. And then we're going to carve off a chunk of those and say, all right, those are the chunk of variables that we're interested in. We're going to draw some boundary around it and say we're only interested in things which are far away, i.e. outside this boundary. And in between there's going to be some noise. And the idea is the noise in these variables is going to wipe out a bunch of information, and it's going to turn out that we only need some much lower dimensional summary f of x in order to summarize all the information that's relevant to the variables far away. So yes?
I'm sorry. I'm having a hard time seeing some of the finer detail on that picture, and I wonder if you could just maybe talk me through it one more time.
All right. First, if you're having trouble seeing anything, I recommend opening up the slides. They're linked in the thought catcher. Second, so going over real quick again, I can hold this a little closer. We have a causal model. So this is like this directed graph here that's telling us how all these variables relate with each other. And that would be something like the mechanical laws governing the dynamics of atoms in a pencil or something like that. We're carving off a chunk of that graph, saying here are the variables we're going to summarize. We're also carving off a bigger chunk and saying we're only interested in summarizing information relevant outside of this bigger chunk. And in between, we have some noise, and these noisy variables are, intermediating between x and y, and they'll wipe out some information. Then the formula is our prediction, i.e. distribution of y given x, only depends on the summary f of x. So p of y given x equals p of y given f of x, as long as y is far away, meaning it's outside of that boundary. So an example of this, a numerical simulation that I ran, in this case, I'm just looking at a linear Gaussian system. So we have a big causal system. These are all little arrows. There's this whole graph of arrows. Each node in here is a Gaussian variable, and the arrows indicate the relationships between them. So like this Gaussian right here is coming from a linear combination of these three plus some noise. And down here, I'm showing the same thing, but it's way more dense. So it just looks black. This has like 1,000 nodes. This has like 50,000 or something. And I carve out 3 little regions within this. And I say, for instance, what information from this region is relevant to that region over there. If you do the math, it turns out that singular components of the covariance matrix are the dimensions which are relevant far away. And when we look at those, we find that they drop off very quickly, meaning for this system, I have about 110 variables in each of these little chunks, but only maybe 3 or 4 of them are actually relevant far away. This was just one particular example I coded up. So you have a 110 variable system. Summary is 3 or 4 variables. Now, we can take the same idea, extend it. This was the sort of 2-variable view. This is the same thing for a whole system. So rather than picking one chunk, we have a bunch of different little chunks that we're interested in, and each of them have some boundary around them that says what's nearby versus far away. And then each of the X variables is going to get its own summary. And this is showing how that works. So we have some X variable here. It has a summary. This summary summarizes everything that's relevant outside of that boundary. That happens for each variable. And there's no further assumptions here, just the same thing as before. It turns out that this is then equivalent to a system where we model all of the far apart things as independent, given their summaries and the interactions between their summaries. So in other words, as long as we're only asking questions about things which are far apart, we can just throw out this whole original model with all the little arrows in it and keep around some high level model that models interactions between the summaries. Excuse me. So for example, in our electronic circuit, these low level variables would be voltages or currents or whatever in lots of little patches of metal or ceramic on different parts of the circuit. And then these high level summaries would be things like the voltage and current in a particular resistor or transistor or something. And this might be one resistor, this might be one wire, this might be one transistor. And we can switch between these two basically for free as long as we're only asking questions about things that are far apart. If I'm asking about like the voltage in this transistor given the voltage in that transistor, well, those are not far apart. They're sort of nearby regions overlap. So I'm going to have to go look at lower level stuff. There may be some crosstalk between those. There may be some radio noise or something. But if they are far apart, like I'm trying to predict the potential in this wire based on the potential in that wire, then I can route through the high level model in order to make that prediction. Okay. And the idea is, since these are lower dimensional summaries, while these are very high dimensional things, doing all the math in the high level model should be much more computationally easy than doing all the math in the low level model. Some fun facts for the category theorists here. We can compose these. So for instance, right here, I'm showing there are some summary variables of these low-level variables. I could have another level of summary variables which chunk together these into new, even higher level variables. And this might be something like a logic gate or logical wires between logic gates. And then these will have some relationship, some new probabilistic model governing them. And this composed abstraction follows this same formula. So as long as this is a valid abstraction and that's a valid abstraction, the whole end-to-end thing is a valid abstraction. Another one you might like, we could abstract these in a different way. So like we could pick out different low-level variables or pick different notions of nearby and far away and end up with different summaries. And a hypothesis which was floated to me was that if we do this two different ways, we should be able to come up with a limit for these two different abstractions. I don't know whether that's true, but this is a hypothesis which I have heard and sounds plausible. And then there's a formula there in case you want to get into the math of this. We may come back to that. Going back to the experiment from before, in the systems view, fun fact, if we took before the summary of this chunk of variables that's relevant to that one, we can also take the summary of this chunk of variables that's relevant to another chunk. And interesting fact, the relevant summary dimensions overlap heavily. So what this is showing is that the first two dimensions of those two summaries are essentially the same. So the same summary is relevant over here as is relevant over there. at least in this particular experiment. All right, that gets through basically the first half of the talk. How are we doing on time? Good. First half was the long half. The next part is going to be talking about how this applies to a couple of like realistic-ish problems, science and language.
Also, just note, John, if it ends up feeling worth it to take like 5 extra minutes, you should feel free to take those 5 extra minutes.
Cool. So, problem in science, you probably won't be able to read this on this slide, but problem in science, we live in a very high-dimensional world. And in general, it's hard to learn things in a high-dimensional world. Calvin and Hobbes flying down the hill on a sled, and we're trying to predict the speed of the sled or where the sled is going to go or something. And if we didn't know anything about physics a priori, there are gazillions of things which could potentially influence the speed of the sled. Like maybe there's astrological forces out there, like maybe the motions of plasmas in faraway stars are going to influence the speed of our sled, or maybe some blades of grass or some wind halfway around the world is going to influence the speed of the sled. Like we have just massive numbers of variables out in the universe, and any of those could, in principle, influence the speed of our sled. And when you think about this, like, how is science even possible when all of these different variables could be relevant? And the point this comic is making is, well, if you only need to control a handful of those variables in order to keep getting the same outcome every time you do the experiment, then that rules out all the other variables in the universe. So like if we can take the same sled, put it at the top of the same hill, and it ends up crashing in the same place, then apparently whatever else was going on in the universe wasn't particularly relevant to this experiment. Okay. And in practice, what we find in science is that usually we can get, or at least in the physical sciences, we can get reproducible outcomes by controlling just a fairly small handful of variables. So for instance, here I've got the Navier-Stokes equations, and we can think about a discretized version of this. So this would be like our grid on which we're simulating some sort of fluid flow. There's the fluid flowing. And what we have at each point in this grid is a small number of summary variables. So a u, that would be the velocity of the fluid locally, maybe a pressure. Yeah, that's it for the simplest ones. Maybe a temperature if you want that. And this is like, 4 or 5 dimensions of variables. And then the actual equation here, the Navier-Stokes equations, is relating those 4 or 5 variables to the 4 or 5 variables right next to it. Like this delta du dt is just relating it to the 4 or 5 variables right next door. And this equation is essentially three dimensional, or there's 3 constraints sort of wrapped into this equation. On the other hand, in this whole system, if we have, say, n dots, then that means we have something like 4 or 5n variables. So a priori, any of those 4n variables could be relevant to predicting what's going on right here. Yet in practice, there's only a handful of them that matter, right? And like if you look at physics, if you look at chemistry, biology, whatever, all of our equations are always low dimensional like this. It's always relating a small number of variables on one side to a small number of variables on the other side. Meaning that empirically, we find that these low dimensional summaries are sufficient to tell us what's going to happen. Make sense? Another way to see why this is interesting is imagine we're trying to predict some variable x1, and there's this huge space of possible formulas or possible physical laws which could, in principle, govern x1. And we're doing experiments to try to figure out which of these physical laws is the right one. And you imagine that each experiment gives us some information. It lets us rule out maybe these laws or it lets us rule out maybe those laws. And you can ask how many bits of information or how many bits of search do we need to narrow in on the right law? And if you think about it, the vast majority of bits of information we need is just to narrow down which variables are relevant. Like in this case, maybe x1 just depends on x2. It doesn't depend on x3 or x4 or x5 or x6 or whatever. Then the vast majority of bits we need are just to establish that fact. Once we know that it's just a function of x2, finding out the actual functional relationship is a lot less work in terms of bits of search than figuring out which variables were relevant in the first place. Make sense? So we see the theme again here is this idea that low-dimensional summaries tell us what we need to predict things far away in some sense of far away. And sort of conjugate way of thinking about it is we are chunking the world up in ways such that low-dimensional summaries tell us what's relevant far away. Let's see, do I want to do this section? Yeah, I'll go through this section real quick. In language, we run into this problem where we don't actually have enough data. Like humans in our entire lifetimes do not receive enough data to figure out what a word means by brute force. So like, if you think about what the word apple means, how much data do you need to figure that out by brute force? Well, like, how many functions are there from, say, a picture to a yes or no answer to the question, is there an apple in this picture? There's a vast number of functions. There's a super exponentially large number of functions from pictures to yes or no answers. How do we figure out which of those is actually identifying apples? Well, we can't by brute force. There basically has to be some sort of prior that we're using to figure out which things are admissible as objects in the world around us in order to communicate as well as we do. And a useful conceptual model for that is this idea that words point to clusters in thing space. So like we go around and sort of cluster the world, and then when we hear a word, we think, this points to a cluster. And this is a useful conceptual model. People have written about this before. It sort of handles a lot of the things that are conceptually difficult about language. But the problem with this is the axes. Like in order to think about clustering, we have to think about the axes of thing space. Like what are the features of thing space? And there's no canonical axes to thing space. That doesn't make sense. The point I want to make here is I think the clusters model is basically correct, except that it's sort of a metaphor for abstraction more generally. So what's interesting about Bayesian clustering is that if I take this point right here and this point right here in the same cluster, these 2 points are independent given the summary statistics of this whole cluster. And this is just how Bayesian clustering is defined. It defines that things are independent given the summary statistics. So what this would say in a way that's not talking about like clusters in a particular space is something like the word trees is pointing to some summary data such that different trees are independent given this summary data. The idea being that this summary is presumably much lower dimensional than the low-level description of all the trees in the world. Yeah. That was somewhat faster than I wanted to get through that, but you can ask questions about it later if you want. That brings us to the last thing, the natural abstraction hypothesis, which is basically the hypothesis that the concepts that humans use on a day-to-day basis, like the objects we recognize in the world, mostly basically work like this. And B, because this whole formulation isn't particularly dependent on anything specific to humans, other minds are likely to converge on similar abstractions for similar reasons. Like the notion of tree is a concept which is useful to have for more general minds in our environment because it saves computation and it's predictively useful. Like because there's this low-level summary that's relevant to everything far away, it is useful to use that low-level summary when making predictions. So, summarize the main ideas here. One, in day-to-day practice, abstraction usually involves finding some chunk of the world that has a low-dimensional summary that contains everything that's relevant far away for some notion of far away. Empirically, looking at like the physical sciences, it turns out that we can usually chunk the world in ways that makes this work. We can usually pick out chunks of the world such that everything we need to know for making predictions far away fits into a low-dimensional summary. I claim that this tells us interesting and useful things about language, and we have this hypothesis saying that this is how most human concepts work. Yeah, that's it. Any